The 5 notes of the pentatonic scale obtained in the previous video are shown on the screen. By the end of this video, you will be able to produce the 12 musical notes used in Western culture. In the previous video, we used the instrument shown in the figure to carry out a search that led to the 5 notes of the C major pentatonic scale over the octave that goes from C4 of 260.74 Hz to C5 of 521.48 Hz. In this video, we will continue this search until completing the 12 musical notes used in Western culture. Remember that the procedure used in the search is the following. The frequency of the last note obtained is multiplied by 3/2 to produce the note separated from it by an interval of a fifth. If the frequency resulting from this last calculation is less than 521.48 Hz, the length of the string is adjusted by multiplying by 2/3 the length of the string corresponding to the previous note, and it is verified in the instrument that the result is pleasant, and if it is, the data of this new note is entered in the table. If by multiplying the frequency of the previous note by 3/2, a frequency greater than 521.48 Hz is obtained, it is reduced to the octave considered by dividing its value by 2, which is achieved by multiplying by 2 the product of the length corresponding to the previous note by 2/3, that is, multiplying this length by 4/3. If we multiply the frequency of the note E4 by 3/2, we obtain a frequency of 495 Hz, which is lower than 521.48 Hz. It corresponds to the note B, identified as B4. So we apply the 2/3 chord length reduction factor to the length 64/81 of L, giving us a length of 128/240 of L. We'll use this value on the instrument. This setting at 128/240 of the string length produces a joint sound of both strings that is acceptable to the ear. We will enter note B4 and its associated data in the table. Note that, to keep the width of the columns in this table, the ratio of the string lengths for this note and those that follow it are shown by their decimal value. If we multiply the frequency of note B4 by 3/2, we get a frequency of 742.5 Hz, which is higher than 521.48 Hz. Therefore, we use the adjustment factor of the length of the string of 4/3 to the length 128/240 of L, with which we obtain a length of 512/729 of L and a frequency of 371.25 Hz corresponding to the F sharp expressed as F numeral 4. Unlike the previous notes, this note is not at a perfect or major interval from the C4 note, but at an augmented fourth interval, which is indicated by the use of the numeral symbol. We will study what is related to intervals and the use of symbols to indicate sharps and flats in later videos. If we multiply the frequency of the note F sharp 4 by 3/2, we obtain a frequency of 556.5 Hz, which is higher than 521.48 Hz. Therefore, we apply the adjustment factor of the length of the string of 4/3 to the length of 512/729 of L, with which we obtain a length of 2048/2187 of L and a frequency of 278.43 Hz corresponding to C sharp expressed as C numeral 4. This setting at 2048/2187 of the string length produces a joint sound of both strings that is acceptable to the ear. We will note this in the table. If we multiply the frequency of the note G sharp 4 by 3/2, we get a frequency of 417.65 Hz, which is lower than 521.48 Hz. It corresponds to the note G sharp identified as G numeral 4. Therefore, we use the reduction factor of the chord length of 2/3 to the length of 2048 2178 of L, thus obtaining a length of 4096 6561 of L. This setting at 4096 6561 of the string length produces a joint sound of both strings that is pleasing to the ear. We'll put it on the table. If we multiply the frequency of the note G sharp 4 by 3/2, we get a frequency of 626.48 Hz, which is higher than 521.48 Hz. Therefore, we apply the adjustment factor of the length of the string of 4/3 to the length 4096 6561 of L, with which we obtain a length of 16,384 19,680 of L and a frequency of 313.24 Hz corresponding to D sharp expressed as D numeral 4. This setting at 16,384 19,680 of the string length produces a joint sound of both strings that is pleasing to the ear. We will note this in the table. If we multiply the frequency of the note D sharp 4 by 3/2, we get a frequency of 469.86 Hz, which is lower than 521.48 Hz. Therefore, we apply the reduction factor of the length of the chord of 2/3 to the length 16,384 19,680 of L, with which we obtain a length of 32,768 59,049 of L and a frequency of 469.86 Hz, corresponding to a sharp expressed as a numeral 4. This setting at 32,768 59,049 of the string length produces a joint sound of both strings that is pleasing to the ear. We will record it in the table. If we multiply the frequency of the note A sharp 4 by 3/2, we get a frequency of 704.79 Hz, which is higher than 521.48 Hz. Therefore, we apply the adjustment factor of the length of the string of 4/3 to the length 32,768 59,049 of L, with which we obtain a length of 131,072 177,147 of L and a frequency of 352.39 Hz corresponding to the note F identified as F4. This setting at 131,072 177,147 of the string length produces a joint sound of both strings that is pleasing to the ear. We'll put it on the table. If we multiply the frequency of the note F4 by 3/2, we get a frequency of 528.48 Hz, which is approximately equal to 521.48 Hz, with a small excess error of 2.73%. We will analyze this result in more detail in the next theory video, dedicated to the tempered chromatic scale. For the moment, we conclude our search by taking as the last note the note C5 of 521.48 Hz that we obtained in the previous video, dedicated to the notes that constitute the pentatonic scale. So we use a string length of 1/2 of L, and again we hear this note on the instrument. We record this last note and its adjustment in the table. Next is the presentation of the notes obtained on the circumference of a circle following the order in which they were generated, that is, by fifths. A regular 12-pointed star is obtained. Unlike what happens in the regular 5-pointed star for the notes that make up the major pentatonic scale, in which the transition from E4 to C5 that completes the star gives the sensation that something is missing, all the transitions are now made by fifths, and we have the sensation that we have a complete system. Remember that, as we mentioned in the previous video, in the theory of scales that we will see in subsequent videos, musical notes are generally ordered in increasing order of their frequencies. Let's rearrange our table according to this criterion. Let's consider again the notes on the circle, and join them in strokes following the order of their frequencies. We will hear the C chromatic scale. We will next present the hours of the day on the circle to establish a relationship between these hours and the 12 musical notes of the chromatic scale. This relationship will be used throughout the theory videos, and forms the basis of what we will call analogy of the clock, which will constitute a kind of map on which we will trace our way through this theory. It is therefore convenient to memorize the position of these notes until we can mentally and effortlessly place them on the clock face. The laborious work we carried out in this and the previous video has resulted in the 12 notes that constitute the basic material with which the Western culture creates its musical compositions. Thanks for watching this video. In a future theory video we will consider the adjustment of the notes obtained in this video, and in the previous one, to generate a chromatic scale that solves some practical problems of the scheme that we use in the generation of these notes, and facilitate the elaboration of musical instruments.